Great. Right, so after this quite intense introduction to Bayesian thinking, basically, we're going to move on to the core of Bayesian inference, and that is priors and Bayesian updating. And in fact, priors are probably the hottest topic in Bayesian statistics, and that is one of the questions that we get most times, like, what about priors? So to go back to the weather example that we've just seen, we are faced every day with probabilities. So, for example, think about the weather forecast, where we could say that there's a 70% probability that it's going to rain tomorrow, or a 25% probability that it's going to be cloudy today. And in this sense, probability is the probability of an event occurring, and we've seen that in the previous session. But what about more complex situations that are not a flip of the coin kind of situation, right? Here, it either going to be raining or not. So, for example, what about rolling two dice? In these cases where you just don't have a flip of the coin situation, a flip of the coin event, this is where probability distributions come in. And probability distributions are really at the core of the whole Bayesian inference framework. And a probability distribution is just a list of values and their corresponding probability. So before we saw that for rain, for the event of raining, there was a particular probability, and that was it. But if there are multiple values that a event could potentially take, and we're going to see some examples in a second, each value will get its own probability. And the list of values with their own probability is a probability distribution, or if you're familiar with Despicable Me, as Gru is saying, it's a distribution of probabilities. And depending on the nature of the values that particular probability can take, we say that there are two types of probability. Discrete probability distributions and continuous probability distribution. I guess most of you will be familiar with these two types of probabilities, but just for the sake of completeness, I will briefly go through them. And as our helpers, minions, are showing us an example of a discrete probability distribution on the left with the orange one, and on the right, you see an example of a sample that comes from a continuous probability distribution. And the two minions on the left say that one says that they have one eye, and the other one that it has two eyes. And that is a discrete probability distribution because minions can either have one eye or two eyes or three or four, and they cannot have any value between these numbers, right? At least in principle. So you can either only have one eye or two, but you cannot have 1.2 or 1.5 eyes. And that's why it's called a discrete probability distribution. It's because within any two values, you cannot have any other value. On the other hand, in continuous probability distributions, since the name is like definitely telling, instead you can have any value between any two values. And in this case, the third minion is telling us that they're 1 meter tall. But 1 meter is an approximation. We don't really know whether if it's exactly 1 meter. It could be 1 meter 0.1 centimeter or 1 meter and 1 millimeter. And in fact, even within these values, you could pick basically any possible number. And that is what a continuous probability distribution is a probability distribution where if you pick two values within the distribution, you can have any infinite number of values between those two values that you picked. So now I'm going to show you some more concrete examples of discrete probability distributions and continuous probability distributions, and you'll see why they're really important when thinking about priors. So I mentioned before rolling two dice, and this is exactly what I'll be telling you for a bit. And so let's assume that you have two dice, one is black and the other one is white, and you roll them, and then you sum whatever the two dice give you. And if we start from the left side of this figure, you see that the only way of getting a 2 is getting two ones. So the black dice has a 1 and the white dice has a 1 as well. And there are no other possible combinations that can give you basically a 2. If you move on to the second column, 3, there are two ways of getting a 3 with two dice. In one case, the black die has 1 and the white die has 2. Or the other way around, the black die can have 2 and the white die can have 1. So in fact, if you have two different dice and you want to get a 3, there are two ways of getting a 3 with those two dice. And if we move towards greater numbers, you can see that when we hit 7, there are actually 6 possible ways of getting a 7. And each combination basically is going to give you a 7. And since there are more combinations that can give you a 7, getting a 7 has actually a higher probability than getting any other number. And you can see that basically visually because this column is the tallest. So a discrete probability distribution is sort of like counting how many ways you can get a particular value. And in fact, if you calculate all the possible combinations that you can get with a black and a white dice, these are 36 combinations in total. And 6 of those will give you a 7, while 5 of those will give you a 6 and an 8, and so on. And to get a 2 or a 12, there's only one possible combination. So in fact, these are probabilities. If you calculate this 6 over 36, it's going to give you 0.16, which corresponds to 16%. So you have a 16% probability of getting a 7, while getting a 2 or a 12 is only 2%. And if you play dice games, I don't, but if you do, perhaps you will realize that that's why a 7 counts less than a 2 and a 12. Another example of a discrete probability distribution is the so-called Poisson distribution, and this is the distribution of counts, for example, like counting eyes, as we were doing with the minions before, or counting the number of fillers that a speaker is uttering during speech. And the discreteness of this discrete probability distribution, you can see it visually by the fact that you have these vertical lines and let's call it a lollipop at the top. And with this discrete probability distribution, you cannot have any numbers between any two of these values, right? So let's assume we're counting eyes. What this graph is telling us is that there's a way higher probability to get a 2 and a 3, basically, eyes, than getting, for example, 6 eyes. And the probability of getting 10 eyes is basically 0. And so here, as we've seen before in the dice example, the higher the lollipop, the greater the probability of getting that particular value. And again, you cannot get values that are between, for example, 2 and 3. And the so these are basically generally the main concepts that you have to remember about discrete probability distributions, and that is basically sort of counting the ways that you can get a possible value and assign a probability to one of those values, and at the same time not being able to get any value in between. On the other hand, a continuous probability distribution works differently from discrete probability distribution. And in fact, you can have any number between any values I was saying before. And because of this, we cannot make a list of all of the possible values. We would just never stop because there are infinite numbers between any two other numbers. So we cannot assign a probability to a specific value. And what you see here is something that is going to come up later. This is a Gaussian distribution, which is also called a normal distribution. It's just two names for the same type of distribution, and that is how it looks like. And on the x-axis, don't mind about the y-axis for now. On the x-axis, you have hertz, and this could be, for example, a distribution of f0, fundamental frequency. And in this case, this particular distribution has a mean of 200 and a standard deviation of 50. And we're going to go back to mean and standard deviation in a second. But for now, just remember that if you pick any of these numbers, if you pick 2, in fact, you could have any number in between. And those numbers are basically an infinite amount of numbers. So since we cannot assign a probability to each and every possible value within that particular distribution, instead, we assign probabilities to a range of values. And if you imagine that the area under the curve sums to 1, so if the area under this particular curve is 1, then you can calculate basically the area within a particular range, and the area, as you would in geometry, so like we really calculate the space that that particular range occupies under the curve of the distribution. If you calculate the area, that is going to give you the probability of getting any value between within that range. So in this example, what you see here is the area under the curve colored in orange, the shaded area, that covers any value that is below 160. So when you calculate the area geometrically, you get basically 0.2 more or less. So this is 0.2 out of 1. And that corresponds to 20%, right? So 0.20 is 20% of the entire probability distribution. So basically, you have a 20% probability of getting any value for f0 that is below 160, right? So again, the important concept here is the range, like a range between two values. Of course, this is on the so-called left tail of the distribution, but we can also do it on the right tail of the distribution. And in this case, you see that the range is between 220 hertz and above. And if you calculate the area of this shaded orange area, that is about 35% of the total area under the curve. And that corresponds to a 35% probability. So getting a value between 220 and above is, you have 35% probability of getting any value above 220 hertz. These numbers are just for pedagogical reasons. They might be more or less sensible, but do not worry about that right now. And now we just looked at two examples where you can have any value that is below a number like 160 or above a number, in this case 220. But of course, we can do the same with a range that is within the probability distribution. And in this example, what you see is the area, the shaded area under the curve between 120 hertz and 210 hertz. And again, if you calculate the area, that would give you about 53%, 52% of the total area under the curve. And that means that you have a 52% probability of getting any value that is between 120 and 210. And this idea of having a certain probability of getting any value between two values is really at the core of Bayesian inference, and we're going to get there later on. So this was just one example of a continuous probability distribution, the Gaussian distribution. It's also called normal, as I was saying before, because it's allegedly very frequent, and it's in fact at the core of modern statistics, basically. But there are other continuous probability distributions that you will very likely encounter when you run Bayesian models. One of these is the beta distribution, and the beta distribution is bounded between 0 and 1. So continuous probability distribution doesn't mean that the possible values go from -infinity to +infinity. And in fact, you can have probabilities such as this one, where the possible values are bound between two values. And with the beta distribution, that is 0 and 1. And in this case, what I basically shaded is the entire probability distribution. And so what this means, which, as I was saying before, if we make that equal 1, then it means 100% probability of getting any value between 0 and 1. So basically, that would cover, yes, sorry, like that's not supposed to be F0 hertz. Sorry for that. So in that case, that should cover basically all the possible values between 0 and 1. So we've seen a few distributions and we've seen a few plots, but how do we, how can we talk about probability distributions? We can list all of the possible values in their probability, as we've seen before, and we can just rely on plots. So in fact, the way of describing probability distribution is to use generally 1, 2, or 3 parameters and set a value for those parameters that give you the shape of the distribution. And I'm going to show you an example with the normal distribution here. That's not the right one. There you go. So again, I'm sure most of you will know this, but the normal distribution has 2 parameters. One is mu, which is the mean, and the other one is sigma, the standard deviation. And if I move the mean, if I increase or decrease the mean, I hope you can see this. What you see is that the distribution slides either to the left or to the right, depending on whether I'm decreasing or increasing the mean. But the overall shape of the distribution doesn't change. And the mean actually corresponds to the center of this normal distribution, which means that is the location where you get the highest probability. And if I set the mean to 0, and I can't really pick it exactly, but let's assume that's at 0, then it means that the peak of the distribution, the center of the distribution, is going to be above 0. On the other hand, if I change sigma, the standard deviation, sigma changes how thin or wide the distribution is. So, for example, if I increase the standard deviation, you can see that the distribution is becoming wider and wider. If I decrease the standard deviation, the distribution gets thinner and thinner. And sorry, when you get it, like when it's very, very thin distribution, it means that any value that is outside of this particular distribution is basically impossible, right? And this will come in handy in a second. So this is important to remember. Every probability distribution has its own parameters, and you will mostly be working with 2, 3 probability distributions, so you shouldn't worry too much about that. But it's important to remember that the normal distribution has 2 parameters, and these parameters help us describe the distribution in a simple and succinct way. So now we know that we need to use parameters, and of course that leads us to some formulas. In this case, these are going to be very simple formulas, and we're not going to do basically any math, so don't worry about it. So what you see here is a formula of a outcome variable. It could be F0, it could be articulation rate, it could be really anything. And the tilde here means this variable is distributed according to a normal distribution. That's why there's normal there. And this normal distribution has two parameters, the mean and the standard deviation. Nothing new here. It's just that this is a formula, but it's exactly the same concepts that we've just seen before. And if you remember the example from F0 before, the distribution had a mean of 200 Hertz and a standard deviation of 50. So this formula is basically just telling you if you sample F0, the values that you're going to get are going to be distributed according to a normal distribution with a mean of 200 and a standard deviation of 50. And this is nothing new. What you see here is the same distribution as you've seen before, but now you probably have a better understanding of why the center of the distribution is above 200 and why the shape of the distribution is the way it is. And again, we're going to delve into sigma standard deviation in a second.